You're joking. Not another one? Oh, for God's sake, I can't stand this.
So the next type of graph that we're going to cover in part 2 is the circle graph. Hopefully you know what a circle is. It's a round thing. It's a locus of distant points from a central point. But what's the formula for a circle? Now, most formulas, they have y equals. This one doesn't. The formula for a circle is going to be x minus h squared plus y minus k squared equals r squared. So what do these mean? It means that the center of the circle is at the point h, k, and it has a radius equal to r. So if we had a circle which is centered on the point 5, 4 with the radius of 2, so if we have our xy coordinate system here, so 5 across, 4 up, so there's our center of our circle with a radius kind of like that. Imagine that I can draw a circle. It's going to have the formula x minus 5 squared plus y minus 4 squared, don't forget the squared, equals 2 squared, which is 4. Okay, what's the domain and the range? The domain and the range, if this point here is h and this one here is k, the domain, that's all the x values, is x is going to be greater than or equal to h plus r. Actually, it's the other way around, isn't it? It's going to be x less than, I should say. Actually, let's do this one, that one there. H minus r, and it's going to be less than x plus h plus r. Sorry, that's a bit messed up there. But see, if this is h and this is r, then that's going to be the tangent there. And the range is going to be all the y values, and I'm going to do it properly this time. K plus r and k minus r. So this is k plus r, that's k minus r. So all of those. So from this we can see that this is not strictly a function, it's a relation. And it has to pass what's called the ruler test. So the ruler test says that if you get a ruler and you have it parallel to the y-axis and you move it from left to right, there should never be a point where there is 0 or 2 or more points where it crosses the graph, the line of the graph, where it intersects the graph. And in this case, it fails in both ways, because if we have our ruler here, it's not going to cross the circle once. But if we have it here, it's crossing it twice, here and here. So it's disqualified both. So that's why it's not a function. So let's do some exercises, some questions related to this. So the first question here, we're told that a circular garden has a center at 4, 3 and has a radius of 5 meters. Write the equation of the circle. The center is at 4, 3, so it's going to be x minus 4 square plus y minus 3 square equals 5 squared, which is 25. Then it says graph this circle. So here's one that I did previously. Paste that in on GeoGebra. So we see here this is x minus 4, x minus 3 equals 25. So here we see our circle, and it's at the center is indeed at 4, 3. Okay, state the range and the domain. So the domain, we're going to take it as being all of the x values. So what's the minimum x value? It's at minus 1. And the upper limit is positive 9. So the domain is between -1 and positive 9. So x must be greater than or equal to -1 and less than or equal to 9. What's going to be the range? The upper limit for the y values is at 8, and the lower limit is at -2 by the looks of it. So the range is going to be between -2 and positive 8. However, your teacher wants you to express the range in the domain. Explain what the domain and the range mean in this context. It means that we can't have y values that are greater than 8, and we can't have y values that are less than -2. We can't have x values that are greater than 9, and we can't have y values, x values that are less than -1. Now notice here we can have multiple values. So for some value of x, apart from right here at the extrema, if we have here at say 0.2, it's going to cross twice. So any point along here is going to cross twice. And likewise, for any value of y that's between those, except for right at the end points here, it's going to also cross that circle twice, here and here. Second question is a wheel. So a wheel is modeled by this equation where x and y are measured in meters. So it's this graph, that circle. So I did this previously while you weren't watching on GeoGebra. So this is what it looks like. Find the center and the radius. So the center, remember the h is 2 and k is 3 because the minus are already in there. So it's going to be centered at 2, 3, and find the radius. The radius is this number, the square root of this number. So the radius is the square root of 9, which is 3. Obviously, we can't have a negative radius, so it's just going to be the positive square root of 9. So if we look at our graph here at the point 2, 3, 2, 3, yep, sure enough, that's the center of the graph. And if we go across 1, 2, 3 spaces, that's going to be our radius. Find the highest and lowest points of the wheel. Highest point is at 6, but remember it's in meters. So the highest point is in 6 meters and the lowest point is at 0. So high and low. Explain why this graph is not a function. So it fails the ruler test. If we run a ruler down there parallel to the y-axis, it's going to cross this graph here and here, which is against the rules. It can only cross it once, and once only for any value of x. And of course, if we run it down here, there's going to be absolutely no values that it crosses that circle at all. So therefore it's not a function, it's a graph, it's a relation. For this last question, I just want to repeat a really nice question that I saw on a YouTube video that I'll link to below. She says that if you have a 3, 4, 5 right angle triangle, so we're going to say this is our right angle triangle, side 3, side 4, and we know using Pythagoras that this side here is 5, inscribed by a circle. I should really say the circle is inscribed by the triangle. It means that the circle is completely inside that triangle, but touching the edges once and once only. Sorry, should be the other way around. And then it says, prove that the circle has an area of pi. And the way that she did it geometrically. She used a geometric formula for the distance between a perpendicular distance between a point and a line. But I thought, let's do this using graphs. So we know we have a circle and we know we have a 3, 4, 5 triangle. So this side here is 3. So this point here is the point 0, 3. And this point here is the point 4, 0. And if you use the x minus x1, y minus y1 equals mx minus x1 formula, you find that this straight line here has the formula y equals negative 3 over 4 x plus 3. It must be at plus 3 because it crosses the y-axis at 3. And it has a gradient of minus 3 over 4. So it goes down 3 for every 4 that it goes across. Which must be true because it drops 3 here and goes across 4 here. Okay. Interesting. We're then told that there is a circle inscribed by that triangle. So we know that a circle has the formula that we've done. So we need to know what that radius and what the equation of that circle is. And if we've got that, then we can say, okay, it must cross it there, here, and here. Not cross it, but just touch that, be tangent to that. How are we going to do that? We're told that the area of the circle is pi. So the formula for area of a circle is, of course, pi r squared. And if we set this to pi and solve for r, so I'm going to divide both sides by pi. They're going to cancel. Divide that by pi. So pi divided by pi is 1. So r squared is 1. So that means that r must be 1. Okay. So far, so good. We know then that the radius is 1. And we know that the left-hand side, the edge of the domain here is at 0. So that means the radius must be 1 across. So that must be at 1. And we know that it's a circle, so it must be 1 up 1 as well. So the center of our circle is at 1, 1. We know the radius is 1. And that tells us a lot. That tells us that the formula for the circle here is x minus 1 squared plus y minus 1 squared equals 1 squared, which is 1. So we want to prove, I'll maybe leave this to you to do that. So we know, therefore, that it must be tangent there. Minus 3 over 4x plus 3, and this line here intersect each other. So I've done the maths beforehand, so this is a graphing question. So what I'm going to do, I'm going to put this in wherever I have a y. So x minus 1 square plus minus 3 over 4 x plus 3 minus 1 square equals 1. And when I expand all of this out and take the 1 over, I get 25 over 16 x squared minus 5x plus 4 equals 0. So if they are tangent where they cross, this quadratic formula, because now this is a parabola, this quadratic formula must have one solution and one solution only. And if you remember your quadratic formula, that means that the determinant must be equal to 0. So therefore b squared minus 4ac must equal 0. If you don't remember that, I'd probably say go back to the quadratic formula videos that I've done. Let's test that. So b is minus 5 squared minus 4 times a, which is 25 over 16, times c, which is 4. Okay, so minus 5 squared is 25. Minus 4 times 4 is 16. 16 times 25 over 16 is 25. That, sure enough, that equals 0. So this circle, therefore, must only touch this line one place and one place only at that point there. We don't really care where it is because we know the quadratic formula is axiomatic and we're going to presume that it's true. Really nice question. The next type of graphs are exponential graphs, and the formula for these are going to be given as in this form here. Okay. So we see something interesting from the get-go. The x is up here in the exponential part. It's in the superpower. So this is where this comes from. It's in the exponential part. It's if you see something like exponential growth, or if something doubles every so and so and so, that's when you would use exponential graphs. So A here I'm going to come to in a while. B here is the growth factor. So think of this, if we say that it doubles, this is going to be 2. If it trebles every time period, we're going to say that it's 3. So this is the amount that we multiply the last amount every time we go. You'll see what I mean in a second. So if we say that this is a growth thing, so this is X is in years, and B was 2, that would mean it would double every year. H is, of course, you should know, same thing. It's going to move it left or right. K is going to move this up or down. So the A here is interesting. The A here is going to be the y-intercept, but it's a conditional intercept. That would be if H was equal to 0 and K was equal to 0. So these are going to have the same shape as long as B is the same. But A would be the y-intercept if H equals 0 and K equals 0. So I'll show you what that means using GeoGebra. So here is an example, and we see this is 3 times 2 to the power of x minus 4 plus 1. So this is the graph 3.2x plus 0, which has been moved to the right 4 places and up 1. But watch what happens when we set k equal to 0 and we set h equal to 0. It's going to cross there at 3. Let's just zoom in a bit there so you can see that it does really cross at 3. As long as 2 is there, that's our growth factor, it's going to have exactly that same shape. So these numbers up here are going to move it up and down and left and right, but they're not going to change the shape. So what's going to be the range and the domain? The range is going to be y is going to be all values greater than k. So it's an asymptote, so it's strictly greater than that. So if we zoom in and zoom in and zoom in, you see there it's it never quite gets there, so it's an asymptote. The domain is all values of x. There's no value of x that we can't put in there that we don't get a y value. Is this a function? Does this pass the ruler test? Yeah, it does. For any value that we go across here that's parallel to the y-axis, we're going to have one and one only place where it crosses that graph. So therefore, yes, it is a function. So the horizontal asymptote is y equals k. So the range is all values greater than k. Strictly greater than, so it's not greater than or equal to k, it's greater than k. Okay, let's do some examples. We have a Malthusian growth function here. So we have population of a bacteria is modeled by this thing here, and it asks us to graph this between t equals 0 and 10 for t. When we put it in GeoGebra, because it's going to be x, and the t is the time in hours. So what does that tell us? It tells us that when t equals 0, i.e. when we start, there were 200 bacteria on this petri dish. Estimate the population after 5 hours and estimate the time when the population reaches 2000. Explain why this is an exponential rather than a linear model. Every hour there is 1.4 times more bacteria than the hour before. So therefore it cannot be linear, because linear graphs increase or decrease by the same amount. Okay, so linear graphs increase by the same amount, but this doesn't increase. It increases by a different amount. In fact, the more it grows, the more it grows. Okay, graph that function. So here's one that I did previously on GeoGebra. It is a real pain in the neck to have these lined up. Okay, so we can see here that it was 200, was it? Yep, 200. So it crosses there at 200. And then it says, estimate the population after 5 hours. Here's 4 hours, 1, 2, 3, 4, 5. So that's going to be 5 hours. So 5 hours is going to be what? 1, 2, 3, 4, 5. So it's going to be around about 1,050-ish. And then estimate when the population reaches 2,000. So we're going to come on here to 2,000, go across, and then come down here. So it's in around about 6 hours and 40 minutes. This would be 7 hours there. If we wanted to do it algebraically, we could always do that. In fact, let's do that. 200. So y equals 200, 1.4 t. So we want to know what the population is after 5 hours. T would equal 5 hours. So the population would be 200 times 1.4 to the power of 5. And grabbing our calculators, 100, 1.4 to the power of 5. 1,075, and what did we say? 1,050. So pretty good. Remember, the scale here is so 1,500 to 2,000. It's going to be pretty. I think we did pretty good there to get within 25. And when would it be at 2,000? So for this, what we're going to do is we're going to set y equal to 2,000. What's my pen doing? And then we're going to solve that for t. Okay, so first thing we're going to do is we're going to divide both sides by 200. So 10 is going to be equal to 1.4 to the power of t. I'll divide both sides by 200. Then what do we need to do? What we're looking for is in the exponent part, so we're going to need to take the log. So log base whatever, 10 is going to be equal to t times log of 1.4. So therefore t is going to be equal to log whatever of 10 over log of 1.4. And we would again use our calculator for that. So brackets log of 10 divided by log of 1.4 and 6.84. So 6.84 hours. Oh, my pen is doing all sorts of funny things. 6.84 hours, which is, yeah, around about 6 hours and 45 minutes. Remember, there's 60 minutes in an hour, not 100. So, yeah, looking at by inspection, it was pretty good. So if you've ever taken your prescription to the pharmacy, in fact, I think now they email them, don't they? Your pharmacist it's possible that your pharmacist will be doing a calculation like this one here, and it's called pharmacokinetics. And it's essentially the mathematics of how medication and chemicals interact with your body, and it's especially concerned with how quickly your body can excrete or get rid of or use up that medication. If you get a medication, you don't take it all at once. You have to spread it out for a couple of reasons. First, it's more effective when you do it like that. It kills the bacteria. But secondly, you don't want to overload your body, put in more than it can handle, and get rid of when it's done its job. So, with that said, we've got the amount of medicine in a person's body is modeled by this. So when I do it in GeoGebra, the T, of course, is going to be X. Where M is the amount of medicine in milligrams, so 1,000th of a gram, and T is in hours. So graph the function between 0 and 12. So I've already done that one. Now notice something interesting about this one. Previously, we had our exponential graphs going like that. That was an exponential growth model. This is now an exponential decay model because the amount of this medicine in your bloodstream is going down over time, hopefully. All right. Estimate the amount of medicine left after 6 hours. Here is 6 here. So it's, what's that going to be? So 6 is there, and it's there, and these are 1, 2, 3, 4, 5. So 11, 12 milligrams. So 12 1,000th of a gram. Next one, estimate when the amount drops below 20 milligrams. So here is 20 milligrams. If we go across here to 20 milligrams, and then we go down a bit. So it's in 1, 2, 3, 4, 5. So it's in around about 4 hours and 50 minutes, approximately. So if there was ever a time where your body couldn't have less than 20 milligrams, you'd need to take your pill every 4.5 hours. In fact, you'd probably need to space it out a little bit more than that when you first start off. Explain why the graph gets close to 0 but does not become negative. It can't become negative. You can't have a negative amount of a medicine in your body. They just would make no sense. But also, if every hour you've only got 3/4 of the amount that you had the hour before, 3/4 of a number which is greater than 0 is still going to be a number greater than 0. So by this model, you're constantly getting rid of this medicine, but you never quite get rid of it after a while. I guess after a while it would be so small that you wouldn't be able to measure it. Just a place of interest, we've got the equation here is at 80 times 0.75, and yep, sure enough, we start off there when t equals 0 at, okay, so for logarithms can be expressed in this way. Y is going to be equal to a log base b, but we're not going to worry about b. We're going to just say that b is 10, so it's the common log base 10, x minus h plus k. And as you can expect, the h again moves this graph left to right. The k moves this graph up or down. The a here is interesting. So the a is the x-intercept if h equals 0 and k equals 0. The b is going to decide the shape. So the higher the b, the more extremer, the more eccentric it's going to be. This is going to have a vertical asymptote, x equals h. Okay, so I'll show you what that means on GeoGebra. So here we have a graph. So this one is 1 times log base 10 of x minus 0. So h is 0 and k is 0 as well. And we see here that sure enough, it crosses the x-axis at 1. This is the only time that it would be crossing it at 1. Notice that there is a pretty amazing vertical asymptote. It goes to that asymptote really quickly, and it goes up here really more and more slowly as we go up. So what is the range and what is the domain? If we say that the domain is the x values, so the domain is all values of x that are greater, okay, and the range is all values of y. Of course, these are all subsets of the real numbers. So why does it have an asymptote at x equals h? If we look at the thing here, we've got x is log of x minus h. If h was greater than x, then we would be taking the log of a negative number, and we can't do that. So that's why there is that really strong asymptote there. So now we have a logarithm question. I'm only going to do one for this. At a school concert, the sound level decreases as a person moves away from the speaker. So hopefully you should know the further away from something you get, the less you can hear it. The sound level is modeled by this, where L is the loudness, the sound level in decibels, D is the distance from the speaker in meters. By the way, decibels gets its name because decibels is a base 10, and deci is 10 scale. It's not because we have a bell and a decibel is like 1/10 of that. It's because it's logarithmic base 10. Health guidelines suggest that sound levels above 85 decibels may be unsafe for long periods. I think a jet taking off is around about 100 to 110 decibels. The Who once had a concert at 120 decibels. So yeah, it's not good for your hearing if you're exposed to a lot of sound, even though the Who are great. Graph the function. So I've done that here. And you can see that it is upside down from what we've done. And the reason it's upside down is because it's now some number negative that. So taking it away means it's going to turn it upside down. So explain why the domain has to be restricted to 1 to 100 decibels, 1 to 100 meters. There is an asymptote here. So according to this one here, so this is going to be 1 meter here, the decibels at 1 meter would be infinity. It would be infinitely loud. Almost infinitely loud, which isn't really plausible. It's not physically possible. And to 100, if you're 100 meters away from something, you're probably going to get ambient noise. You're going to be able to hear the traffic around you probably, or something else. It's probably, in reality, it's probably going to reach a point there and then it's probably going to drop dramatically again. Use your graph to estimate the distance from the speaker where the sound level drops to 85 decibels, i.e. where it's safe. So here is 85 decibels about here, and that's here at around about 8 meters, so approximately 8 meters. If I move twice as far away from the speaker, the sound will half. Let's look at that. If that's true, then that would work every time. So here we're about 18 meters. So if I move twice as far away, so if I go to 36 meters, which is around about here, clearly this hasn't dropped in half. That's the drop there compared to this whole thing. So clearly it's not. If it was dropping by half, it would be an exponential. So if it was half to the power of the distance, then it would half, but not in this case. The school wants to mark a safe listing zone where the sound level is no more than 85 decibels. Based upon this graph, where should this zone begin? 85 is around about 8 meters, so just to be on the safe side, let's say that it's 10. So I'd say around about 10 meters is safe in the short term. You wouldn't want to be exposed to 85 decibels over the long period. Next up, we have square root graphs. So square roots can be represented in this way: a times the square root of, sorry, my computer is just doing really strange things today, x minus h plus k. And as always, h moves it left or right, k moves it up or down. So the a here is the type of shape that it's going to have. So the best way to show you that is to use an actual example. So let's bring up GeoGebra. So here I have the graph 1 times the square root of x minus 1 minus 0 plus 0. So a is 1, h is 0, k is 0. So notice here the domain is limited because we can't take the square root of a negative number and get a real answer back. We would get complex numbers and imaginary numbers. So it comes down here, and then unlike the logarithmic graphs, it just dies, it just stops. So when I change a, let's change a from 2, let's change that to say 3, and watch what happens to the graph. So it's going to move out there. It's going to get big. It's almost like we've given it growth, some growth pill or growth spell or something from Mario Brothers. Those mushroom things that grow the players there. If we move k here, so let's get that back to where we were before. If we move h here, I should say, and I'm going to move it to the right 3 spaces. So therefore, we've got that. So we can see an asymptote there quickly. And if I want to move it up 4 places, I'm going to do that. So it comes down here and it hooks around and then it just disappears. It stops. So what's going to be the range in the domain? The domain is going to be everything from here to the right. So it can't be anything less than that. And the range is going to be all the values greater than that, but not less than that. Last question is square root 1. So we're told that we have a graph y equals square root of x minus 3 plus 2. Graph the function. So let's bring up GeoGebra because I've already done this. That's what it's going to look like there. So here is our graph here. And we can see that it, sure enough, it's been moved to the right 3 places. Here's 2 and 4. And it's been moved up 2 places. State the end point of the graph. The end point of the graph, I should have said before, is at h, k. So it's going to be at 3, 2. That's where it's going to have its end point. And sure enough, we see that it's right there. State the domain and the range. The domain is going to be all numbers greater than, all numbers greater than 3, and the range, which is the y values, is going to be all the numbers greater than 2. Explain how the graph has been transformed from the graph x squared. So here's square root of x, sorry, I should say square root of x or x squared. It's moved to the right 3 places and it's moved up 2 because h is 3. The negative there says that it's moved to the right, and the plus 2 means it's moved up 2 points. And that's that. Hope you enjoyed that. Good luck with your assessments.